of the for computer science aspect of logic. So, we did logic programming, we have done Tableau methods, algorithms, resolution methods, okay. And today we will do something that has always given my first year students, whenever they have had the misfortune of having me as teacher for programming, headaches. Yeah. So, let us look at that. Okay. So, we will actually look at it in a very simplified fashion. In first year programming, the kinds of proofs that you have to do are very specific to those programs and those algorithms, and therefore, they have to be done in much greater detail, but we will look at it again, we will take a higher level viewpoint and we will just look at the theory of program verification. Yeah. Okay. So, that is what we will do today, and it is actually an extremely small capsule summary of program verification from the point of view of hand proving of programs. I will at some point either today or the next lecture, I will actually talk about the automation a little bit, but I will not go into it in great detail. Yeah. Okay. So, we are looking at verification of imperative programs. So, what we will do is, like we have always done, we will take a very small signature basically, and we will think about imperative programs again as parameterized on some signature. Okay. So, that means we define a while programming language. Okay. A while programming language is very simple. It just contains it's imperative, so it has to have assignment. It has to have sequencing of instructions. It has to, well, it has a conditional, that is not necessary because, but it has to have a looping construct. So, it is non-recursive program. So, we are just considering a simple version of non-recursive imperative programs, and just because case analysis is very common, I have also put in a conditional. Okay. So, this epsilon is the equivalent of having a no op in hardware, okay. And it is there mainly okay, for two reasons which I will come to. So, you have the usual assignment. So, you have some simple variables. Okay. Notice the color coding. We already have two languages, right. You have the language of terms based on some signature sigma, which is in violet in color. Okay. Then we have the language of predicates based on that language of terms, and those predicate names are all in green in color, the operations are in green in color, right. And now we are defining a programming language on top of these both, except for one small difference, it does not encompass the whole of first order predicate logic. Okay. It uses only quantifier free predicates. So, essentially it uses only Boolean operations on the propositional operations on predicates, but the predicates are first order predicates. I mean, they have got parameters, free variables and so on and so on. Right. So, you take the quantifier free fragment of first order logic and you have the notion of variables and you have the notion of an assignment. Okay. And this just says that this term t is assigned to this variable x. Okay. And we have sequencing of programs. So, unlike an actual programming language which has a program header and this and that and blah blah blah, we are getting rid of all of those and just having the most essential notation that is necessary to be able to compose programs. Yeah. So, this semicolon here is a composition operation. I mean, please do not mistake it for the semicolon in C, where the semicolon in C is a terminator of an instruction. Okay. So, you can think of that semicolon as part of every instruction. Every instruction can be thought of as a regular expression of the form something dot star ending with a semicolon in the case of C, whereas here the semicolon is actually an operator. It is a sequencing operator. The effects are not very different, except that in the last command of a program you should not have a semicolon. This is exactly, so this semicolon is very much like the semicolon in ML when you compose a sequence of let us say commands or functions. Yeah, when you sequentially process some functions, maybe you keep, let us say you give a sequence of print statements, let us say in ML, then they will all be separated by semicolon, but the last one will not have a semicolon, because the semicolon is an operator which composes. Yeah, it is a composition operation equivalent to function composition. Okay. So, that is that. This bracket, square bracket, is just a bracketing mechanism. Just in case I need to be able to group things in a certain order, I want brackets. So, I have a pair of brackets. Okay. This is the conditional, very much like you see formulas in spreadsheet programs. When you open MS Excel or whatever, and you want to give a formula with an if then else, then basically you have a Boolean condition chi, which is a quantifier free formula, okay, which might be a quantifier free formula on the variables that you are interested in. And if it is true, then this program P is executed, and if it is false, this Q is executed. So, this is essentially your basic if then else, okay, right. And this, the next one is just the while statement, okay, the indefinite looping that you have in imperative programs, non-recursive indefinite looping. So, this says that while chi is true, essentially do P, and this star essentially says that you keep doing it indefinitely. Okay. Simple programming language. This programming language is sufficiently powerful to encode any universal Turing machine. I mean, so for example, we do not have functions and so on and so forth. You do not have things like for loops, because for loops can all be rendered as while loops. You do not have pointers, of course, that is one big problem in terms of things, but otherwise its computing abilities are equivalent to any standard computer. Okay. Things may be less efficient or more cumbersome to do it this way than through other ways, but it does not reduce the power of computation in any way. That is the important thing. So, this is a very simple programming language called the while programming language. It has been very popular in most treatises on in the beginning verification of programs. Okay, since almost all programs can be expressed in while. In fact, for the purpose of provability, it is better to translate all programs into while and then prove them, rather than keep them in their native form, okay, for certain reasons. So, this epsilon no op actually is present in every programming language in some form. So, for example, in C, if you just put an open brace close braces, that is your epsilon. In any assembly programming language, there is a no op, and in particular if I want just the if then construct, okay, then I use the if then else with Q being epsilon, right, and so I can, and then of course I can compose things. But the more interesting thing about epsilon, algebraically speaking, is that epsilon is the identity element for composition. Okay. So, epsilon semicolon P is the same as P, that is the intention. P semicolon epsilon is the same as P, even if P is not terminating. I mean, now with the concept of a programming language, there is an issue of termination which we have to address at some point, but so P semicolon epsilon is the same as P, and so on and so forth. Yeah. Okay, so essentially this, the set of programs defined by this programming language forms a monoid under semicolon with epsilon as the identity element. So, it has a nice neat structure. Okay. So, when we look at a programming language, and when we look at programs, we think of them as essentially transformers of state, right, a state transformer. So, what happens is you essentially have some memory. Okay. You have a memory bank of which you are using, let us say, some part. Okay. And what you do through a program is there is an initial state of this memory, and by program of course, we do not mean an interactive program. We are talking about programs which have just which start from some initial state, and if they terminate in some final state, and state is essentially the memory map that you are using. For all practical purposes, we can assume that this memory is infinite. Okay. And what this program does is it essentially transforms the memory map. Okay. In the case of this while programming language, it does not use any extra memory. Okay. There are no declarations, no ways of getting new variables, program variables and so on. Okay. And so, essentially what happens is that the picture of memory remains more or less the same, except that the values stored in those locations are now probably different. Okay. So, a program is essentially a state transformer. Okay. So, it has a fixed set of variables, and we will identify those variables with the variables of logic. Okay. Actually what happens is that those variables in a memory are really abbreviations or names of memory locations. However, we will not take the notion of a memory location very seriously. We will just take it as, so therefore, the notion of a state of a program as the contents of the memory that is being used by the program is now identified with just a valuation. So, the state of a program in an actual machine refers to transforming memory maps, even for a small while programming language like this. If you implement it, it will actually transform memory maps, but we are not bringing in the concept of memory, we are just looking at it as valuation, the memory map itself as a valuation of variable. Okay. And essentially as a valuation which takes valuation in the same sense in which we defined the semantics of first order logic, the semantics of terms in first order logic. We had a valuation which was essentially the set of variables arrow some values in their domain. So, it is essentially a variable to value mapping, right. So, you have a domain, you have a domain bold A, and essentially take the carrier of this bold A. So, your bold A is essentially something of this form, there is a carrier A and based on sigma, yeah, right, on your signature sigma. So, at this moment sigma is just some parameter. So, it is given an arbitrary signature of terms, I can define a while programming language parameterized on that signature. I mean, in fact, that is what happens with all your higher level software. You take MATLAB for example. The basic constructs of MATLAB are all like imperative constructs, assignment, this, that, blah, blah, blah. You take object oriented programming, your basic assignment, looping, sequencing and conditional, they are all there. The signature is expanded, it is not just whatever signature is there in the bare machine, The bare machine has a signature, basically whatever operations the machine allows, let us say arithmetic operations and so on and so forth, integer arithmetic operations, real operations, floating point operations, whatever. That is the signature of the bare machine itself, but when you have something like MATLAB, you actually have, you can deal with entire, you can deal with lots of structures, MATLAB, Maple, Automath and so on. So, you can deal with entire structures, and given any complicated structures, we can define a while programming language on top of that. Yeah, in that sense, it is absolutely general purpose and very highly polymorphic on the signature. Okay. So, program is merely a state transformer, and so of course, you defined a language, then we have to define its semantics. So, for all practical purposes, this is the semantics.
Why does it
well, I chose a star because you might have 0 iterations. Yeah, but that depends on the state, right? Whether it is going to be 0 iterations or not. It depends on the evaluation of chi.
So, if chi is evaluated, isn't it the first iteration?
No, 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 no. 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 So, actually it is you take any while loop, if the body executes k times, then the condition is evaluated k plus 1 times. Okay. That's very clear. Okay. So there is a k plus 1th checking of the while loop before you exit the while loop. So that's why I used star, but that is only notation. Everything depends on the semantics. Yeah. So here is the semantics. We have to define a semantics. In the case of this simple language, we define essentially what is known as a denotational semantics, functional. It's completely defined by functions rather than what we normally do in a course on programming languages, which is you define the low level operations and then a big steps, a small step semantics and then a big step semantics and so on and so forth, right. Here I am taking a more simplified view. I am looking at all this as a pure state transformer. Think of it as a black box state transformer. So you actually are taking this program. Think of this program now as there is this program, it is a black box, and we are not dealing with memory anymore. The semantics of this language is defined as essentially I start with a valuation and that valuation V A is the input, and what it produces is a new valuation V A prime, and each of these is a function from the set of variables to the carrier of the domain in which you are looking at. Yeah. Yeah. So, this is what a completely black box picture. So, it is the biggest step semantics based on just structural induction. Yeah. Okay. So there is this notion of meaning. So, a program is a state transformer. A program of course is just a piece of syntax. So the meaning under some domain A of this program P is something that transforms V A to some V A prime, where V A and V A prime both belong to this bold V A, which is the set of all possible valuations of variables. Yeah. Okay. So these valuations are also called states. Yeah, in the case of an imperative programming language, and that's you have states. Okay, and of course, everything that satisfies every element of this is a program. right. Every full element of this structure is a program. So, you can compose, you can add programs, concatenate programs and so on and so forth. You can do all that and get fresh, it is closed under this composition operation for example, yeah, which is not true of most actual programming languages, because they have a program header and this and blah 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 and some terminator and so on and so forth. So, you can't just take one program and concatenate another program blindly to it, you have to do some other work also for it. Okay. So, the empty program just leaves the state unchanged. The assignment, it creates a new state, okay, in which the new valuation is exactly the same as the old valuation, except possibly for the value given to x. And the value that is being given to x is that you evaluate the term t under the old valuation V A, whatever value you get from that, you give that to x. Remember that this V A, all these other terms which I am not explaining are exactly as we have done before in the semantics of first order logic. Okay. So, this V A is something that comes from the time when we define the semantics of terms, right. Okay. In the case of a bracketed program, if you add an extra pair of brackets, you are not doing anything. The meaning of this program is exactly the meaning of the program without brackets. Okay. So, that finishes the some of the simplest constructs, and now you have this semicolon. As I said, semicolon essentially means that, so what we are saying now is that you take this program, you take two programs P and Q, since it is closed under composition, what we are saying is you take this, you give a valuation V here, V A here, you think of this valuation itself as an input to the program. After all, programs work on memory, right. So, they work on valuations, okay. And this P will give some, will return, will result in a transformed valuation V A prime, which is the input to Q and which gives me a new valuation V A double, right. Okay. So, this is essentially, so this is completely functional, a functional style of defining. So, essentially if I take the meaning of P, okay, and evaluate it in A, I get V A prime, and essentially I am going to take the meaning of Q and compose it with this and evaluate them both under V A. So, this semicolon is exactly function composition, okay, which is fair enough, which is what I said. Okay. So, it is now as far as the conditional is concerned, it is very simple. This conditional is a quantifier free formula, and of course, your valuation deals with all the variables, right. So, it is possible to evaluate this condition chi for truth under the valuation V A, and if it is true, then the new valuation that you get is whatever you get by executing P on V A, and if it is false under V A, then whatever the new valuation that you get is whatever you get by executing Q. That is the semantics of Ifthenelse. Yeah. As far as the while loop is concerned, it is very simple. You first evaluate this chi. If it is false under the valuation V A, then of course, it is exactly as you said, it just returns back the same valuation. So, the result is the same valuation V A. If it is true, then this while essentially acts like the replication operation in the lambda calculus, right, like the Y combinator. So, what does it do? It spawns a new copy of the body of itself, and the body is executed in composition with that, right. So, on demand you spawn a, it is like spawning a new recursion, while and recursion are essentially the same. Yeah. So, it spawns a new version of itself and executes that after having executed the body, right. So, that is this while is not entirely structurally inductive, but I will not get into it. Yeah. There are structurally inductive ways of specifying it as a fixed point and so on and so forth, but we will not get into it. But we have essentially given a black box view. So, essentially what happens is that it spawns a copy of itself and attaches to the body at the end. So, the body is executed and again it goes into it goes to execute the while again. Yeah. So, this is a recursive definition. So, this is an intuitive semantics of the while programming language. However, the problem now is you can take, the point now is where does logic come in and where does verification come in. Here we said that a program is essentially a state transfer, right. Given a certain VA, it gives you a certain VA prime, right. There is also another way of looking at it. You can think of a program also as a property transform, right. So, what I can say is I have a program P and basically I am not interested in any particular valuation and how it's of course deterministic, this language is deterministic, and therefore it is possible to give a functional semantics for it, but it is not necessary to think of it as a state transformer, because most often we are not interested in the individual states, in the individual valuations. We are not interested in all possible valuations, each component of the valuation. You are not interested in the value of each variable, for example. What you are usually interested in is that I have a whole collection of memory maps. Okay. Think of this green box as essentially the set of all possible valuations. Okay. So, essentially this bold VA, think of it as this bold VA. So, it is the set of all possible valuations, of which there is some subset, okay, of this valuations which satisfies some property phi. Okay. Then what we are saying is there is in the what the program does is that it actually gives me a new valuation satisfying probably some slightly different property, or not slightly, satisfying a different property. So, there is some subset of this VA which satisfies some predicate psi, and essentially what I am saying is that this program as a state transformer, what it does is it takes, let us say, an element starting from phi as input, and as output it gives me an element satisfying psi. Okay. So, rather than worry about individual valuations and individual variables in valuations, we are looking at properties. Okay. That is the fundamental basis on which all program verification based on first order logic is defined. So, we are only worried about properties, we are not worried about the values of individual variables. Okay. We might be basically what most of the time what are we doing in a program? If you think of if you remove I/O from the program and make every program purely functional, single input, single output, then you have some, let us say it reads the input from some area of memory, let us say all the variables that require to have certain values, then the variables bear certain interrelationships, of which you are interested in only a small set of those interrelationships, and that set of interrelationships that you are interested in is defined by this phi, and what you are interested in achieving is some other interrelationships between those variables, and that is what you specify by psi. You are not actually interested in tracking individual variables except when something goes wrong with your program. Yeah. So, the values of other variables which phi and psi may not mention at all are of no interest as long as the program does what it is intended to do. And what you want to show in program verification is, given a specification of properties phi and psi and given a program P which claims to do that, you want to be able to verify or you want to be able to prove that the program P starting from some state which satisfies phi terminates in a state that satisfies psi and is always guaranteed to do that. So, for example, it should not happen that you start from some state inside phi and go off into some other place, that should not happen, right. I do not have, okay, let me, right. So, that is a no. Okay, that is a no. The other thing is, what you are saying is that if it starts from some state outside phi, then it really does not matter where it goes. Okay. So, if you give this as input and it goes off somewhere here or it goes off into this also, it does not prove anything. Okay. But something like this going off like that is a no. What you want to show is that given that there are no bets outside phi, I do not care what happens if the input is from outside phi, but what I am saying is if the input is from phi, I want a guarantee that it ends up if at all in psi. So, in that sense programmers are not just state transformers, we can elevate them to property transformers. So, the properties of a valuation are changed by changing the valuation appropriately. Yeah. Okay. So, these are they can also be called predicate transformers. Yeah. So, this phi, so what is known as a partial correctness assertion essentially consists of this phi which is called a precondition and this psi which is called a post condition. And what you are trying to say is that this program P satisfies this precondition and this post condition, and you write this as a triple in this form, and this triple is called a partial correctness assertion. Okay. So, what we are saying is that in any state V A, this triple holds if the initial valuation V A actually satisfies this phi. So, that you are starting with that assumption that I am restricting my attention to this blob phi. And now, the program of course has a semantics which transforms states into some new valuation V A prime, and what you are saying is that if it does give me a new valuation V A prime, then that A V A prime should satisfy psi. Notice that this is implies in the sense that it does not say that this thing would necessarily have to go to a final state. The program may not terminate. So, here essentially what you are saying is, if the program execution does terminate and it gives me a new state V A prime, then that V A prime must satisfy psi, right. That is what this is about. Then we would say that this phi p psi is a valid formula in A, and this is denote we use the usual validity notion. Okay. We have extended it to the programming language with partial correctness. If this holds for every initial state V A. Okay. So, the first thing actually this first bullet actually tells you about satisfiability of this triple form of this Hoare, what is known as a Hoare triple, yeah, after Tony Hoare who actually gave us this, right. And the second one talks about validity, and actually we are most often interested in validity. Notice that we are not interested in validity in a domain independent fashion. We are interested in validity for particular domains A, which are particular sigma algebras. So, unlike logical validity, I have not gone to that logical validity which would say that for all sigma algebras A, this should be true, this should be valid. No, we are not saying that, and that is that we are restricting ourselves to validity in a given domain, because normally when you talk about a programming language, the given domain is actually whatever the underlying machine can represent as a model of, let us say, numbers, for example. I mean, for example, your machines are not going to represent non-standard models of the naturals, right. I mean, they only represent one particular model of the naturals, one particular model of the integers, and so you are interested in validity only within that model, right. Okay. So, that is what. So, now programs therefore are predicate transformers, and this is the concept that was probably hardest for people to understand in first year in my programming courses. But the important thing here is that this only defines partial correctness. Okay. As I said, this one says that if the meaning of P under V A is a valuation V A prime, then V A prime should satisfy psi. It does not say necessarily that the meaning of P under V A should be some valuation. And one of the important things that we are interested in programs is that they terminate, and that is the notion of a total correctness. So, we will use this notion of total correctness, and moreover total correctness also depends intrinsically on the underlying A, right. I mean, you have to come up with well orderings and so on and so forth. In A, you have to define a measure of descent on a well ordering, on a path of the on a well ordered path with a finite, which means it has to, that should not be an infinite chain, it should be a bounded chain, right. So, this total, so this A is validity is always with respect to a given algebra A with a given carrier set. Okay. So, a total correctness assertion is a triple with by the way, these are black square brackets, right. I mean, they are different from the blue square brackets which are part of the programming language. Yeah. Okay. This so phi p psi. Here again phi is the precondition, psi is the post condition, but here what you are saying is that unlike in the previous definition, here you are saying that firstly this phi should hold in the initial valuation V A, and the very fact that phi holds in the initial valuation V A must imply that the program does terminate from that valuation. Okay. So, the difference between partial correctness and total correctness is really that, take these two scenarios. So, I have the program P and I have essentially one blob phi here and another blob psi here, and in the case of partial correctness, for which I will use blue, for which I will use green, what we are saying is that given a valuation here, it can go into a valuation here, or given a valuation here, it can go, it should not terminate. Okay. So, if this is my set of all valuations, it really goes outside the set of valuations, because it is like an undefined state which is outside the valuation. Yeah. So, this is perfectly valid for partial correctness. Okay. For total correctness, what you are saying is that this is not acceptable. Yeah. What you are saying is that for every such thing, it should actually go into this psi somewhere. Yeah. Okay. So, in general what you are saying therefore is that when you look at total correctness, there will be only a subset of this, there will be only a subset of these phis which guarantee this property, and essentially what you are saying is that they are outside this subset, but still satisfying phi, what you can have is this. Yeah. Okay. So, your notion of phi therefore is circumscribed by whether you are interested in partial correctness or total correctness. Okay. The notion of validity again is exactly the same. It is just that this definition has two parts, where there is the and is here and the implies is here, and this definition has implies first and then an and. Okay. The meanings are of course different. Okay. So, this is what we have as the main notions of specification. So, in a specification ideally from now on when you are asked to write a program, we should just be able to give a phi and a psi in first order logic, and you should write the program, and you should be able to prove that your program without executing it. Without executing it, you should be able to prove that phi, that the program satisfies the specification phi psi, where phi is the precondition and psi is the post condition. Right. So, here let us take a, we have to, I mean all programming begins with factorial. So, let us start with factorial. So, what we are saying is this is a simple imperative program, and of course, there is no IO, there are no program headers, nothing. So, there are two variables in this program, x and p, okay, and basically think of this program as something that reads in the value of x from somewhere, or it has the value of x pre-specified. Okay. So, and then what happens, the actual program initializes p to 1, and if x is greater than 0, then it executes, oh yeah, then this is a while loop. Yeah. this whole thing is a while loop. What does it do? It p is assigned p star x and x is decremented by 1, right. So, we will assume that all these operations are all available and so on and so forth, all these relations are available in the underlying domain. So, your signature includes all these things. Yeah. Then what we are saying, remember here, then this is a partial correctness assertion. This partial correctness assertion says that if x is originally greater than or equal to 0, then p is going to be equal to factorial of x. Actually, what I should, okay, I should change this. Okay. Unfortunately, in the case of programming, since valuations change, variable values get updated. So, we should actually state this partial correctness assertion in this fashion. There is an initial value of x. So, x equals x naught greater than or equal to 0, p, and of course, I am assuming integers, right. There is an implicit assumption in there. P equals x naught factorial and x is and not x is greater than 0. This should be the correct partial correctness assertion. So, ignore this for the moment. Yeah. Yeah. So, this is the partial correctness assertion which this program satisfies. Notice it is a partial correctness assertion, because if x is negative, okay, the program does not terminate. Then the precondition does not hold. Oh, it is total. I am sorry, it is total because if the whenever the precondition holds, it actually terminates. Okay, let us write a partial correctness assertion where supposing we change this to true, what happens?
Something x naught but not greater than 0.
Oh, okay, yeah. We'll just change it to x equals x naught, yeah. But not not necessarily greater than or equal to 0. Yeah. Then you get a partial correctness assertion. Okay, right. So, of course, the main question now is how to prove this.
No, sir, but it is not a partial correct, because then it will be p is equals to 1. Because if x is less than 0, then p will be assigned 1.
Yeah.
And the condition that x is greater than 0 is falsified. So,
oh, okay. So, it will actually terminate. It will always terminate. So, this program always terminates. That is a problem. Okay, that is a problem. Okay. So, I should not have. I should have thought of something else. Okay. Anyway, at the moment, let us just look at this as a partial correctness assertion. Yeah. Okay. But the question is of how to prove it, and you have this language, and therefore, now what we need to give are proof rules for this programming language. Yeah. So, that is the so here are the rules for partial correctness. Okay. So, this set of rules for partial correctness is approximately structurally inductive. Okay. Basically, there is one rule for each construct of the programming language. Okay. So, the empty program basically does not change any state. So, any property that holds initially as a precondition also holds finally, right. Okay. So, that is what. So, this actually does not transform the predicate phi at all. Okay. Next we come to this assignment, and here is So, what we are specifying here is that supposing there is some post condition psi which needs to be satisfied, then an appropriate precondition is one that is obtained syntactically from psi by replacing all free occurrences of x by the term t. So, this phi and psi are full first order predicates. They could have quantifiers in them, they need no and they could have free variables also. In particular, the program variables will be free variables of all your assertions. Okay. There might be other bound variables, but they will not necessarily be part of the program. In particular, what happens is you might want to make an assertion, supposing you take the prime number generation program, at a certain stage, let us say after I iterations, you have found the first I primes. Okay. Then your I is a counting variable of the program, which let us say keeps track of the number of primes that have been generated. But you will have a bound variable for your assertion which says for all j less than I, pj has been generated. Okay. So, there will be bound variables, so there will be quantifiers also, which essentially says that I have computed all the first I primes, and that statement requires a universal quantifier, and it requires a bound variable for the universal quantifier, but that bound variable will not be a program variable. Okay. So, the free variables are what will be program variables, right. Okay. So, this one says, so therefore, if phi actually has x as a free variable, of course, it is quite possible that phi does not talk about x at all. Okay. In which case, I am sorry, let us say psi, let us say psi does not talk about x at all, then of course, the result of this substitution, then x will not be a free variable of psi, and the result of the substitution will just leave it as psi. Okay. But if psi does have x as a free variable, then what we are saying now is, before the assignment was executed, if I replace all those free occurrences of x by the term t, then in that current valuation, in that valuation of the precondition, in that state, phi should, that psi with t for x should have been true. Only if that is true can I claim after the assignment that psi would be true. Yeah. Okay. Is it already time? Ooh, okay. So, we will continue with these proof rules next time.